Hello everyone. In this module, we can discuss the probability of error for binary FSK system. In the last module, we have calculated the probability of error for BASK and BPSK. Now, before proceeding this, you have to consider, let us assume, the probability of error for optimum filter. We already calculated in the previous module. So probability of error is expressed as half ERFC of x01 of t minus x02 of t divided by 2 root 2 sigma, where x01 of t minus x02 of t divided by sigma represents the output SNR. And we also define the square of output SNR rho max for optimum filter as rho max is equal to x0 of t by sigma whole square, where x0 of t is the change in the output signal and sigma is a change in the output noise component. And this can be related with respect to the input magnitudes as integral minus infinite to plus infinite x of f square divided by SNI of f df, where x of f represents the change in the input signal magnitude in frequency domain whole square divided by SNI of f, where SNI of f represents the PSD of input noise component. Because we are assuming the input noise as white in nature, SNI of f is uniform, and that it is uniform and it is independent of the frequency. And we are assuming that magnitude as n0 by 2. So that's why let us replace SNI of f as n0 by 2. And because this is independent of frequency, let us take outside the integration. So down to the denominator you have n0 by 2. So in the numerator you will have 2 by n0 reciprocation. Integral minus infinite to plus infinite x of f square dx. First, let us calculate the square of output SNR and get the root of that square of output SNR. So you will get output SNR and substitute in probability of error to get the probability of error for BFSK. So let us start with the calculation of square of output SNR, which is expressed as 2 by n0 integral minus infinite to plus infinite x of f square df. Now let us replace this term in frequency domain to time domain. By using Parseval's theorem, you can do that. Integration of square of a particular function in frequency domain, and the magnitude is same or equivalent to that of integration of square of the same signal in time domain. So let us replace integral minus infinite to plus infinite x of f square df as integral minus infinite to plus infinite x of t square dt with that bit interval as tp. So that's why we have taken integral limits as 0 to tp, where x of t, remember x of t is the change in the input signal, which is x1 of t minus x2 of t, where x1 of t is the positive magnitude of the input and x2 of t is the negative magnitude of the input. So rho max can be defined as 2 by n0 integral 0 to tp x of t square dt, where x of t is x1 of t minus x2 of t. And remember that for FSK, x1 of t, that is when the input data bit is 1, you will have change in the carrier frequency to a higher magnitude. So that's higher magnitude, let us assume it as capital omega. This is for data bit 1. For data bit 0, the carrier frequency is reduced by an amount of some magnitude. Let that change in the magnitude be again capital omega. So plus omega represents higher frequency for data bit 1 and minus omega represents the lower frequency for data bit 0. Please substitute x1 of t and x2 of t in the expression of square of output SNR, which is equal to 2 by n0 integral 0 to tb root 2 ps cos omega c plus omega t minus root 2 ps cos omega c minus capital omega into t whole square dt. So this whole thing is in the form of cos a plus b minus cos a minus b. So let us take root 2 ps as common and let us simplify this square of output SNR. So rho max can be expressed as 4 ps by n0 integral 0 to tb cos a plus b minus cos a minus b. This can be expressed as minus 2 sin a sin b, where a is omega c and b is capital omega. So 2 sine omega ct into sine capital omega into t, where capital omega represents a small change in the carrier frequency. So here you have 2 square. So 2 square into 4, that is 4 into 4, 16 ps by n naught, integral 0 to tv, sine square omega ct into sine square capital omega t dt. So minus whole square, it will be positive. So this is in the form of sine square x. So you can write it as 1 minus cos 2x by 2. So we obtained it as 1 minus cos 2 omega ct by 2 into, for this sine square capital omega t, you can write it as 1 minus cos 2 omega t by 2. Once this is applied to the low pass filter at the receiver section, low pass filter does not allow the second harmonic of higher frequency, that is carrier frequency. But this capital omega represents the change in the carrier frequency, which is a very minute factor. 2 omega t component. dB into 1 minus cos 2 omega t dt. This can be written as integral of cos 2 omega t, that is sine 2 omega tb divided by 2 omega tb. Just we have applied the limits from 0 to tb. And for further simplification, let us take tb as common, because you want to write ps into tb, that is bit energy. So 4 ps into tb divided by n naught into 1 minus sine 2 omega tb by 2 omega tb. And our intention is to maximize the square of output SNR. So here this factor can be maximized only when you consider 2 omega TB as 3 pi by 2. So if you consider this value as some other different angles, our SNR is low, and it is high only for this 2 omega tb equal to 3 pi by 2. So rho max is equal to 4 ps into tb by n naught into 1 minus sine 3 pi by 2 divided by 3 pi by 2. Sine 3 pi by 2 is minus 1. So 4 ps into tb by n naught into 1 minus of minus 1. So it is plus 1 by 4.712. So upon simplification, you obtained it as 4 into ps into tb by n naught into 1.21. So finally, you obtained rho max as 4.84 EB by N naught, where EB is the bit energy, which is equal to PS into TB. But you need output SNR to substitute in probability of error. The output SNR can be obtained by taking the root of rho max, that is root of 4.84 EB by N naught. This is our output SNR expression for FSK. Here, if you want to compare this, output SNR for BFSK is more than BASK, because in BASK you obtained it as root 2 EB by N naught. And also it is less than BPSK, because in BPSK it is root 8 EB by N naught. So magnitude is greater than ASK but less than PSK. And now let us substitute the probability of error, the output SNR expression in probability of error. x01 of t minus x02 of t by sigma is root 4.84 EB by n naught. Let us substitute, and you will get P probability of error as half ERFC of 2.2. If you take 4.8 root 84 root, that is 2.2. 2.2 root EB by n naught divided by 2 root 2. So this is half ERFC of 0.77 root EB by n naught. Take this 0.77 inside the root. So it is half ERFC of root 0.6 EB by n naught. So this is the probability of error expression for FSK. If you want to compare the probability of error for FSK when compared to ASK and BSK, in BASK you obtained it as half ERFC of root EB by 4 n naught. So here probability of error for FSK is less than BASK, but it is more than BPSK, because in BPSK it is half ERFC of just EB by N naught. So because the probability of error of BFSK lies in between ASK and BSK, the output SNR will also lie in between ASK and BSK. So it is preferred over ASK, but less preferred over BSK. So in this module, we calculated the output SNR, which we obtained it as root over 4.84 EB by N naught, and probability of error as root 1 by 2 ERFC of root 0.6 EB by N naught. In this module, we completed the two tasks. In the next module, we are going to continue with the probability of error calculation for QSK. Thank you for listening.